Okay, in this last video of new material for this section, we're going to do the final topic for rotational inertia, and that is known as the parallel axis theorem. This is brand new to AP Physics 1, and I really am glad that it's here. This is a nice melding of the two previous videos, and so the idea behind the parallel axis theorem is, in this course, you will take one of the derived expressions for rotational inertia, where the axis of rotation is at the center of mass, and then you will use it to determine a new value for rotational inertia when that same object is rotated from a different axis. And so, to be as ridiculous as possible, I have stolen my son's lightsaber, and I'm going to talk about baseball briefly. So, if you play baseball and you need to choke up on the bat for some reason, so in baseball or softball, that would be like maybe the pitcher throws very quickly, and so you need to make sure that you can get your bat around fast enough to make contact. Or if you're in a game situation where you really need to make contact, you want to be able to swing as quickly as possible. So instead of holding the bat, I'm really good at videos, instead of holding the bat at the bottom, you would hold it up higher. And by doing that, you are changing the rotational inertia of your bat and lowering it so that you can get the bat around faster. So, sorry for that distraction. And so that's something that you would be expected to do using the parallel axis theorem. So on your equation sheet, this parallel axis theorem goes like this. Iota prime, that would be the new rotational inertia, is equal to iota of the center of mass plus the mass of the object times a distance d squared. D is the distance between the center of mass and the new axis. So, to say that again, the rotational inertia at a new axis is equal to the rotational inertia when rotated around the center of mass, plus the mass of the object times the distance between the center of mass and the new axis squared. This is on your equation sheet, so you don't need to look it up. And again, it's just a useful tool where you can use one of those derived expressions and then adjust it to find a new rotational inertia just by moving the axis. So we're going to do an example. This object is the most common example for the parallel axis theorem, but it can be any object that is rotated around a different axis. A thin rod rotated about its center. So this solid line is the thin rod. If you rotate it about its center, then its axis cuts through the exact center. And this rotational inertia, which you would be given, is 1/12 the mass times the length of the rod squared. So that's your old rotational inertia. Now, what we're going to do is, instead of rotating it around its center of mass, we're going to move that axis to the very outside. So we're now going to rotate it around one of the end points. So that axis has just moved a distance d. Now, direction doesn't matter. The value of d doesn't matter as far as direction goes, at least the way that this is constructed, right? Because if you're starting at the center of mass, then that's actually like a location where the rotational inertia is at its lowest, and so no matter which way you move the axis, the rotational inertia is going to get higher. The only other measurement I want to have up here is the length of this rod is L, and so you'll just need to use that in your derivation. So this is essentially a derivation with rotational inertia. So we're going to use the parallel axis theorem, and it actually starts out really simple because you're going to find this new value for rotational inertia. You're going to plug in the old one, so 1/12 m times L squared. And then you just have to be a little bit clever to figure out how to plug in L into this other term. So you add the mass of the object, which is m. It's always a repeat. That actually gives you like terms. And then the distance that the axis was moved, well, it was in the center, and now it's at the edge. You've essentially moved it half the length of the rod, and so it's going to be L over 2 squared. And so now it's your job to combine these like terms and find the new value. And that is always going to require you to understand fractions. So let's work through this together. So 1/12 ml squared plus 1/2 squared is 1, oh, that's 1/12, sorry. 1/2 squared is 1/4. And that's going to be ml squared. So what I have to do is 1/12 plus 1/4 ml squared. Those fractions are like terms. Some of you are much more skilled with fractions than I am. I'm going to go a little bit slower. I need to make these two fractions have the same denominator. So I'm going to take 1/4, and I'm going to multiply that fraction by 3 over 3. That will give both fractions a denominator of 12. So 1/12 plus 3/12 ml squared. Now I can add the numerators. That's going to give me 4/12 ml squared. I can reduce that fraction, and so the new rotational inertia is 1/3 ml squared. And so that is the new larger rotational inertia based on the new location of the rotational axis.